Yo, students, this is Mr. Bornheimer. Today, we're going to go over the gas law's 6 scenarios that I had assigned you to complete for homework. So today I want to talk about these various scenarios, and I want to just quickly recall what the different uh, gas laws are. So we have Charles' law, Boyle's law, and GL's law. In Charles' law, we're going to have constant pressure. In Boyle's law, constant temperature, and in GL's law, constant volume. So let's go ahead and take a look at what we're going to be working with today. You can see here on the screen that I have scenario 2 up. In scenario 2, George is going to go into space, okay? But George is not quite, he's not very bright because he wants to go into space without a suit on. Uh-oh. So what we have to kind of determine here is what can we hold constant, and you can probably already see that there are actually 2 possibilities here. The one thing that won't remain constant is pressure. So the other 2 things that can be held constant are temperature or volume. These are the 2 things we can hold constant. If we hold temperature constant, this is going to be Boyle's law. If we hold volume constant, it's going to be GL's law. Now, in Boyle's law, if you go back for just a second, okay, if you're starting with a person that has lots of pressure and you go to outer space where there's no pressure, you start at a high pressure situation and you move to a low pressure situation. Okay, so we're moving in this direction, which means that there would be a rapid expansion of volume. All right, so basically what a rapid expansion looks like is the person would kind of like blow up. Not very good. On the flip side, in this particular situation, if we're looking at GL's law, okay, you're starting with a high pressure situation, you're going to a low pressure situation, so you're moving down this line. So you'd be going from a high temperature to a low temperature situation. So in this particular scenario, George would freeze to death. Okay, so 2 not very good scenarios for George. You could have held constant volume or you could have had temperature held constant. So you could have chosen Boyle's or GL's law for this particular problem, and both could technically be correct. All right, scenario number 3. In a refrigerator, there is a unit called an expansion valve. Okay, it allows gas to expand, hence its term. It takes a liquid called a refrigerant and allows it to expand from a small volume to a large volume at the same pressure. And really, it's allowing it to expand into a gas. So it starts to turn into a gas, and then that gas expands rapidly. Okay, so the volume here is changing, but it's happening at the same pressure. So the key idea here is that we are going to hold pressure constant. And the law that correlates to this would be Charles' law. Now, Charles' law is a direct relationship. Which means that as one thing changes, the other changes in the same way. So if it goes from a small volume to a large volume, okay, that means volume's changing. The only other thing that can change here is temperature. So if we see an increase in volume, this direct relationship tells us that we'd also see an increase in temperature. Okay, if we were to uh, decrease volume, we decrease temperature. But in this particular situation, there's an increase in volume, so there's an increase in temperature. Okay, that's what would happen to the gas or the refrigeration liquid in a refrigerator. All right, scenario number 4. Bob is working in a pressurized suit with a fixed and constant volume. So this one's pretty straightforward. Before we even go too much further, we know it's a constant volume. That makes it Boyles Law. Okay, all of a sudden the pressure in the suit drops. Okay, again, Boyles Law is also a direct relationship, which means that whatever happens to one of the variables, it will also happen to the other. So if we see an instant drop in pressure, okay, then what we're also going to see is an instant drop in temperature. All right. Moving on, scenario number 5. A PEEP, which has a lot of air in it, is placed in a vacuum tube where the air is slowly removed. This in turn decreases the pressure. The temperature stays the same inside the container. That line right there is really important. The temperature stays the same inside the container. Okay, that is our constant. So temperature is constant in this particular problem. All right, Boyle's law deals with constant temperature. Now, the interesting thing about Boyle's law is it's an inverse law, which means as one thing changes, the other thing does the opposite. So a PEEP is placed in a vacuum tube where the air is slowly removed. Okay, this in turn decreases pressure. So the first thing we know that's going to happen here is that there's going to be a decrease in pressure. And because this is an inverse law, that automatically corresponds to an increase in volume. So in theory, the PEEP should get larger. Last but not least, scenario 6 is very similar to the scenario I gave you in class. A hot air balloon is heating up and expanding. Okay, the pressure inside the balloon is remaining constant. So we know that pressure must be constant. This is going to be Charles' law. All right, and because the hot air balloon is heating up, there's an increase in temperature. Again, Charles' law is a direct relationship, which means that whatever temperature does, the other variable that can change will do the same. Pressure is being held constant. That means volume must be the other variable, and it's going to also increase. Because again, this is a direct relationship. All right, so that's how this works. The computer's taking a quick minute to kind of catch up here. So one of the things that I want to kind of draw your attention to then is just this idea that you need to know these gas laws. Know the types of relationships: direct, inverse, direct. What one thing does, the other thing does the same thing. Inverse, what one thing does, the other variable does the opposite. So direct is kind of the same, inverse, opposite. All right. All right, now we're going to switch gears for just a second. All right, here we go. So what we're going to do is we are going to go ahead and look at a demonstration I'm going to do in class. This demonstration is going to involve a couple of different things, but here's kind of our ingredients list. We're going to need a bottle, a water bottle, that is small. Okay, so we're just going to go ahead and kind of draw this bottle. like so. All right, the next thing that we're going to need for this particular demonstration is we're going to need some water. All right, and I'll explain why, but the water is going to basically go in the bottle. And the last thing we're going to need is some dry ice. And dry ice is technically frozen CO2, so carbon dioxide. So carbon dioxide in the solid state, and this is important. Okay, so what you do, and what we're going to do, is we're going to take a bottle and we're going to fill that bottle with just a little bit of water. Okay? And the reason we're going to do this is because this water is going to be at roughly room temperature. So the water is going to be at room temperature. All right, now what we're going to do is we're going to take chunks of this dry ice. We're going to put those chunks inside of the water. Now you have to remember, dry ice is very, 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 very cold. Okay? So when it hits this room temperature water, it's like jumping into boiling hot water. Like if we were to jump into something super hot, okay? Or if we were to put an ice cube in boiling water, immediately what's going to happen is this dry ice is going to immediately start to change state, okay? Except that CO2 doesn't really go to a liquid state. CO2, dry ice, goes directly to a gas. So what's going to happen is the CO2 is going to start to turn into gas CO2. Now, one of the things you always have to be very careful about is if you have a liquid, like liquid nitrogen, liquid oxygen, CO2, these substances like to be in the gas state. Okay? When they expand or when they fill up and when they start to take up space inside a container, they want to push out in all directions very quickly. So this CO2 is no longer confined to its rigid solid state. It's going to start beating on the side of this container to try to get out. Think of it like this. If you take a bunch of very, very small creatures and you put them in a very tight space, okay, you hold them there. Okay, and then you say all of a sudden you let them loose. Okay, they're going to try to escape. The more creatures there were, the more force they would have, the more better chances they'd have of escaping. It'd be like putting a bunch of students in a room and shutting the door and saying, get out. Okay, well, if one person kind of hit a wall or whatever, wouldn't make much of a difference. But if we had 400 students in a room and they all started beating on a wall, they could probably knock the wall down, depending on the wall. So that's what's happening here. You're taking CO2, you're allowing it to turn into a gas, okay, because it's sitting in water, which is relatively warm by comparison. And there's so much gas that the bottle can no longer hold it in. And so what's going to happen is there's going to be a massive increase in pressure. Okay, so massive increase in pressure. So what we're doing with this gas is we're taking this gas and we're heating up this gas. We're seeing a change in pressure. The one thing that we're trying to hold constant here is we're trying to make sure that we have a constant volume, meaning that we're We're trying to contain it inside a bottle. So if we go back to our gas laws, we see a constant volume would be GL's law. Okay, so if we look at this in terms of the dry ice example, the dry ice starts at a low temperature, very, 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 very cold. And as we increase the temperature of the dry ice, or as we increase it from a very cold gas to a warmer gas, we see a drastic increase in pressure. Now, if the bottle is not strong enough, what we'll see is that eventually the pressure will get out. And this is a very visible and noted demonstration for this one reason, that the pressure oftentimes exceeds the bottle's ability to contain that pressure. I have to give a word of caution here. If you use a bottle that is too strong, this becomes incredibly dangerous. Not just loud, okay, but really, really, really dangerous. Anytime you're working with high pressures, there's always the potential for pieces to go flying, for people to get hurt. So I do not recommend that anybody do this at home. We use a special type of bottle with an incredibly thin wall, so that only a little bit of pressure will cause it to kind of expand and blow apart. And one of the things that you would never really want to use is, you don't really want to use 2 liters. You don't want to use thick plastic. You don't want to use any container that's going to have that's going to build up pressure that is too high. Okay, so just a word of caution. You have to be really, really careful here. All right. All right. Final thing that I want you guys to do, okay, is I want you to think about a couple of different scenarios in terms of these gas laws. Okay, the first scenario that I want you to kind of write down in your notes, okay, and this is to help you study for your test next week, is which laws are, or I probably should say, represent direct relationships. Okay, which laws represent direct relationships? Okay, and I want to be very specific that it could be law or laws. Okay, the second question I want you to be able to answer is the following. Which law or laws represents an inverse relationship or ships? Number 3. Okay. Please give an example for each of the 3 laws not discussed in class or in your notes. So what I really want you to do is I want you to come up with your own examples, one example for each law, kind of like my 6 scenarios. Okay? Last but not least, number 4. Right? I want you to go ahead and I want you to list the 3 ISO words and write a quick definition or explanation for each. This needs to be done in Google Classroom. I will post a place where you can write these four, the answers to these 4 questions. Make sure you go ahead and type them and get them turned in. They will be due Monday when we return to class. So thanks for watching, and I will see you all on Monday.